My name's Edmond. I've been programming for about 20 years, both applications and systems programming. Erlang for about 10 years, mainly in business information systems, banking, messaging, and recent health messaging. The last 2 years, I've been at a company called Medical Objects in Australia, doing working on health messaging systems in Erlang.
Hello, everyone. I'm Roshan Giri. I've been a system and application programmer for over 5 years. I've spent over 2 years doing GPU programming using CUDA for fluid dynamics and simulation for an automotive company in Japan. And for the last 2 years, almost 3 years now, I've been using Erlang at Medical Objects to do some server developments with Edmond. So Medical Objects is an Australia-based company that provides secure messaging for healthcare sector. The messages in the healthcare adhere to a standard known as HL7, and that is what we follow in Medical Objects. And just to give you context, secure messages in healthcare means that the messages that are sent between different facilities in the healthcare, like when you go to a doctor, he asks you to get some x-rays, and the messages that are interchanged between the facility, the practice, and radiology, those messages are the ones that we're handling, and those messages are the ones we're referring to. And Medical Objects is one of the fastest growing companies in Australia and has expanded its services to New Zealand as well. And with that came the need for scaling some systems, and for which we're using Erlang, and Erlang is also being used for other new products, among which monitoring and profiling are also ones. And in this talk, we are going to now in this talk, we are going to discuss process info heat maps and process status flame graphs. Now I'm focusing on status because we have grouped the processes by their state, if it's running, waiting, or runnable. This was crucial because what we found out that in an just to give an example, if we are not grouping them by these things, then if there is like a gen server wait, which is taking the entirety of the flame graphs, then you wouldn't know if it's actually waiting or doing something, and the insight that it may provide may be misleading. Next, we'll also be discussing on why profiling at different levels of load is important. Now, just to say that systems behave differently on different levels of load, be it high, be medium, or be it low, and we're going to discuss on that. And finally, we're going to discuss about how eliminating concurrency-related bottlenecks are more effective than optimizing sequential code.
Just a quick shout out to previous work here that inspired our work, Vlad Kier's eFlame, and Scott Fritch's update to eFlame, where he added stack tracing. Stack sampling. Vlad's was using tracing. Ours also uses samplings like Fritch's, but we do sampling quite differently from him. And of course, you could look up at Brendan Gregg's work at Netflix. He pretty much defined the invented flame scope, flame graphs, and heat maps.
Now let's jump right into it, because the most motivating example that I can give you is how easy it is to use Flameprof. So to generate some profile data using Flameprof, all you need to do is Flameprof start, and you give an argument. Now this is one of the many ways you can use Flameprof. Now here what you are saying is just auto select the top 100 processes and monitor them for 5 seconds, and then on the next 5 second mark, get another top 100 process. So, and we'll collect the data and we'll write it into the file, and until you call Flameprof stop. While doing this, all the data is written, and you can read those data using a fork of Flamescope, which is developed by Netflix, of course, and we have a fork of that in which we have modified it to support the data that we are generating. Now, what we generate and how the Flamescope gives you the data is in this form. So this is the heat map that we show. Now, the test that we performed was performed from 0 to 20 seconds, and at 5 second mark, we increase the load. So that's why you can see that it's gradually increasing. Now, to understand this, the data collected is represented in a time series data. Now, each column there represents a second here. and the rows represent the subsecond, which are 20 milliseconds each. So if you follow one column from top to bottom, that is the view of a single second's 20 millisecond each. Now the colors are obvious. The darker red you see, more of the resources are being used. Now one exception here would be the memory, where you will see green, which would mean that in that 20 milliseconds column, more memory was freed than it was being hogged. So when you try to select some of these and generate the flame graph, you will see a different result. Now this is the representation of the stack traces as flame graphs. Note that they are grouped by status, so you know what is running, what is waiting, and what is runnable. Unlike heatmap, the width here does not represent time, nor is it a fixed value. So the width is relative to the use of resource. So to say, if there are like just two processes, say, and one has 2 reductions and the other has 8, then one will occupy 20% of the width and the other will occupy 80% of the width. Whatever the numbers are, if it grows, similarly, so it's just relative. And you see in the graph at the very bottom, that's the initial call. While moving up the stack, those are subsequent calls, and the leaf representing the last call. So, and even in this example, you can easily see that the logger there is taking quite a bit of resources. Now moving on.
So the one question is why do you profile? And typically the answer you'll hear is that you want to identify code that you need to optimize and code that you need to eliminate bottlenecks. We advise to take a slightly different approach, and the reason we think that this is jumping ahead slightly, and the reason why we say this is because here you're assigning tasks without any goals, and you can very easily end up in a bottomless pit where you're optimizing forever. So it's very important to define the reasons why you're profiling with particular goals in mind, and then you optimize and eliminate bottlenecks in order to reach those goals. There's 7 reasons why. There's 7 reasons that you could use to define your goals, the reasons why you profile. One may be your system is underperforming. So you have particular performance requirements and the system is not performing, is not meeting those requirements. Another reason is because you have a catastrophic performance threshold beyond which you cannot beyond which the system is no longer responsive. Then the other reasons also are quite obvious. The better you use resources, the more money you save. The last reason is slightly interesting, which we found is that when profiling is easy, developers get more intimate with their code. They know where time and space is spent. There is a quote from Joe Armstrong which I quite like in this regard, which is that there's no such thing as fast, there's only fast enough. So on the left here, of course, you have Usain Bolt who runs at something, I can't remember the exact speed. I know he sprints. And on the right there, we have the world record holder for the marathon who runs at around 20 kilometers per hour. So how do you define fast? It depends on context, and you really have to define what that context is for your system. So what is fast? What is fast enough? What is performant enough for your system really depends on what metrics you're using to measure performance. It could be requests per second. That's typical of web-related systems. It could be transactions per second. It could be a frame rate, if it's a video processing system, or it could be response time. So you have to define what these are. And one insight we found, which was quite interesting, is that systems profile very, very differently at different levels of load. So we advise that you get yourself a load tester to generate the appropriate stress levels needed for your goals. You have to define what your goals are, how many requests per second you actually want you want to be able to provide for, and you have your load tester generate that load. And when it's generating that load, that is what you profile. And an example of this we use Sung, so this is an example configuration file for Sung. A little bit contrived, but it illustrates the point. So we have 4 phases in which we generate load for 5 seconds. At the first phase, we're generating requests one every half a second, then every 200 milliseconds, every 100 milliseconds. Then we go to something quite insane where we're generating a request every microsecond. Now, the result of that is if you see the 2 heat maps, so at the top there you have 0 to 5 seconds, 5 to 10 seconds, 10 to 15, 15 to 20, each of those representing the different phases. So if we are to highlight 0 to 5 seconds, which is very low load, versus on the right there we have 15 to 20 seconds, which is extremely high load, and this is the delta of the reductions, you will see something interesting, which is that under low load, the flame graph looks something like this. Of the top, by the way, this was sampled at the top 100 processes sampled for 20 seconds. So what's interesting here is that you can see you have a lot of waiting. You have the gen server loop. What you see in the brackets there, that first call, it's not really a stack frame. It's what we call a pseudo stack frame that's been inserted in order to better group the call stacks so that you know which processes are making those calls. And you can see we have a couch aggregator there doing a lot of waiting. We have the OTP logger overload protector spending a lot of time waiting, and then you have actually code that's running is actually our sampler. Now that's under low load. Now if we look at under high load, it is completely different. We have the processes that are waiting, the call stacks that are waiting now. You can see we have a yours acceptor pool there. We have the OTP overload protector for logger also there. And what's interesting is that we now have some suspended processes. The suspended processes are processes that are waiting for ports, for port programs. And for our particular case, we use PGP, as you can see in the call stack there. And then the running processes are processes that the Erlang VM is actually running. And you can see the call stacks of the top 100 processes that are running on the system. So the point we're trying to make here is that when you profile at different levels of load, you will see the subsystems on your system behave differently. Logging will behave differently. Your web server will behave differently. All the different parts of the subsystems in your system will behave differently, and you'll get very, very different profiles. So that's why it's important to profile at different levels of load. Moving on, for the case where you're looking for some sort of catastrophic threshold beyond which your system no longer performs, here we're talking about knowing your limits. And you can look at this in 2 tenses. You can look at it in past tense, that things went very badly when you got to a certain level of performance. And here you're talking about something has happened in production, and you want to know under what circumstances that thing that happened in production happened, and you will want to profile. You want to use Flamegraph to profile in order to identify the suspect call stacks. And things in future tense, things will go very badly. Then what you're doing there is you're using your load tester to generate to continuously increase load until your system fails, so that you know what your catastrophic performance threshold is for tuning your deployments. And of course, developer resources cost time and money. Computing resources cost time and money. So that might be one reason to profile, is you want you have only a limited set of servers and you want to squeeze some more performance out of them again, but you really have to have targets. The other interesting reason, and this is something we found it was quite surprising, is that if you ask, before we started this project, we asked ourselves, do we really know where time and space is spent on our production systems? And we really couldn't give an exact answer. We could give an educated guess, but we couldn't give a really good answer to know for sure where time is spent. So if you can have an easy tool, a tool that helps you easily identify where time and space is spent at the system level, not at the micro level, at the system level, then this has huge benefits. You can use it, for example, to guide refactoring. If you're going to introduce new components, you know beforehand whether or not a component is going to replace something that's in your critical path, or whether or not it won't matter so much. For example, if you're choosing a new database. And if you can try. We haven't yet done this, but we have done some experiments with this. If you can try and make your profiles part of your continuous integration, so that developers know when they push code, they know whether they're affecting critical paths or not. But you have to be careful, because it's very easy to get into a place, an unhealthy place, where there's a bit of bigotry about code being pushed and its impact on performance. So again, when we're profiling, we're trying to identify identify what to optimize and what bottlenecks to eliminate in order to reach our goal. And for the case of software, you're looking at time and space, and you want to know what part of the system or subsystems, what they're doing when these resources, time and space, are being expended. Typically, the way most profilers, at least the ones we've come across for Erlang, approach this from a perspective of function calls. So you'll have a tool like fprof, and it will give you counts of functions and maybe how much time has been spent on those functions. Flamegraphs are different. Flamegraphs don't focus on calls. Flamegraphs focus on call stacks, and that's a very, very important distinction. And it's based on the observation that if you want to know what a system is doing, the call stacks are more useful than the individual calls. So as an example here, we have two call stacks. They're related in that the first three calls are the same, but the tail, the head of the call stack is different. And so we have on the left, we have call stack A, and on the right call stack B with an additional call. This is to the pretty printer. So if you combine these, if you could combine these in some form, you'll end up where plus there means combine. You end up with something that looks like this, and you can intuitively sense what that means. It's combining the two call stacks in a way that makes sense if you just look at it. And that is in a nutshell what a flame graph is. It's combining call stacks. However, rather than just combining two stack traces, if you can imagine a folder containing thousands upon thousands upon thousands of stack traces, how would you combine that in a way that visually, in a way that you can see what's going on? And that's essentially what a flame graph is.
Right now, so now we have seen the results. Now let's see how we actually sample. So we take regular snapshots of the call stacks for selected process, and then for the given period of time, we actually profile them. And there's actually 3 steps that we go through. We select the process, and we have 2 ways to do that, which I'll discuss in the later slides. Then once the processes are selected, we call Erlang process info on those processes. Now the data that we collect for all those processes, we regularly flush that into the file system. Now I say regularly, but we do a delayed writes, so that we just write once every 20 seconds so that we don't exhaust the IO system so much. So profiling. While we talk about the manual profiling, this one is interesting. So First, we need to start the sampler. For that, we call just flameprof.start. At this point, we just have started the sampler and we're not profiling anything. When you want a manual selection, you need to get the process that you want to profile and then call flameprof profile start on that process. And until you call flameprof profile stop, that process will be profiled. And you can stop the profiler all at once by calling flameprof stop. Now, the interesting thing about that is you can actually call flameprof profile start at any number of processes in your system. So you can have 10, 20, 30, or as many processes you want to profile and get the results on. Another interesting fact about that is we also have an additional argument that we have added, which is called viral. Now, when you say viral, you select one process, it will start profiling that. But again, any processes that it touches, it will start profiling that as well. So you get like a tree structure of profiling process, and all of them will be profiled and you can get the results. Now, we would recommend using this only when you have identified one particular process that is actually costing you a lot. And when you do that, you can actually see a detailed view of what is actually being spent in that process. Now, the next, what we actually recommend you guys to do is use the auto one, because this is an educated guess, rather, let's say that we are getting the most busy 100 processes or any number of processes that you provide the argument with. So all you need to do is auto select top 100. That means select the top 100 process and sample them for 5 seconds. And then at the end of the 5 seconds, you get the top 100 process again. And at the end, you just call flameprof.stop. Now, when you do this, all the files will be written to your file system and you can use Flamescope to just view the results. As easy as that.
Now, the flameprof process sampler, what it does is we frequently, I think every 11 milliseconds, we sample call stacks and we insert what we call pseudo stack frames, the stack frames you saw initially earlier. And what that does is give you better categorization. And then we also include the reductions, and we use the reductions as a metric in order to affect the heat map saturation, that's the color, and the width of the graph, the flame graph stack trace height, the stack frames. So that means that makes it such that the wider the stack frame, the more CPU time the particular call that you're looking at is taking. And the other thing we do, which is a little different from previous attempts to do flame graph profiling in Erlang, is we focus on process status rather than PIDs, because PIDs, individual processes, are really not that useful in Erlang. What you want to do is you want to group processes based on some sort of criteria, and the criteria that we use is the process status, which is whether they're running, whether they're suspended, whether they're garbage collecting. This is a status value that the VM internally manages as it's sort of like a state. You can think of it as a state machine that each process inside the VM goes through. And we insert pseudo stack frames for these in order to have the grouping that we showed earlier. Now, the other interesting thing is that another metric that we use as an alternative to reductions are various other parameters that you can pass to the process info BIF. For example, memory, message queue lengths, the number of GCs, the number of blocks that is being allocated for the heap, etc., etc. And then we use these as alternatives for heat map saturation and flame graph widths. And a good example to show, I wonder if we have enough time. If we're running out of time, Roshan. Okay, a good example is we can show here. Let's have a look at memory. So we already showed reductions, but let's look at memory. So green there, green saturation means that more memory was allocated. Red memory was freed. Red means more memory was allocated. We're looking at the delta of memory, which is the memory BIF processing for BIF. That's how we get the values. And if I select any of these, I get the different call stacks. I get positive and negative. Negative means that okay, we get two additional groupings, positive and negative. Negative means that these are call stacks where memory was freed. Positive means that these are call stacks where memory was allocated. So if I'm interested in memory allocations, I can look at these, and then I get the different process statuses for those call stacks. Now we also do have an experimental version of this, an experimental branch that provides more information. It's not quite ready, but it should be ready in the next week or so, where we further group the call stacks by inserting pseudo stack frames, and we group based on a logarithmic scale. So these, for example, here, if I want to know call stacks that are allocating tens of megabytes, that's positive. I select here, and I can see those that are waiting. So these are call stacks that are waiting, and at the time that those samples were taken, there was the processes had a memory delta that was in the tens of megabytes, running something similar. So we found that this is very useful in debugging memory issues, heap issues. You can also get similar flame graphs for message queue lengths. Right, moving on. General things that we've discovered. We've discovered that, as we've discussed earlier, you should always profile at different levels of load. And one interesting thing is a common pattern you see in a lot of example code for profiling is you'll see someone writing a little micro benchmark, making some sort of requests in that micro benchmark, maybe in some sort of tight loop, and then profiling that tight loop. And what we stress is that at the system level, that doesn't really tell you anything, because it's like you're trying to run at Usain Bolt pace all the time, yet that's not what you'll see in production. So we really encourage you to have some sort of goal-oriented approach. Have a load testing environment that can generate different types of load, low, medium, and high, and that will depend really on what you see off-peak during production, or what's normal during the production, and what's high during production, and generate profiles for these different levels of load. The other thing we found, and this was interesting, is how costly logging is, even with the new OTP logger. And the reason for that, we found, was mainly because of I/O. There is an I/O pretty printer. So if you're logging, for example, if you're using the disk logger that comes with OTP 21 and newer, it's going to format strings and log them to disk. And you'd be actually quite surprised how costly that is. And what we ended up doing is we ended up writing an alternative that rather than writing strings, it writes terms. Actually, we based it on the old log MFH. If you recall from the Sassel days, we based it on that, and we just added, we used an implementation that is logger OTP21 friendly. And I can just give you an example of the result. So this is a screenshot of our OTP logger, which doesn't use strings, which uses which writes terms, and we were able to generate a load of the high rate of 600 of about 460 requests a second. Yet using the standard OTP logger, we were only able to get to 175, and this is something that we found. So that's just something to keep in mind. Logging is actually quite costly. The other thing we found is you need to really focus on concurrency bottlenecks, and this can have a huge impact. So, for example, this is a profile of CouchDB. We'll show memory, and CouchDB has a component called IOQ. Use IO, and we found that ends up being quite costly. So we wrote a patch to CouchDB that bypasses this IO queue, because what happens with IO queue is all the IO requests are routed through the single process, so it becomes a bottleneck. So we wrote a patch of CouchDB, that doesn't, so if you see there's no IO queue anymore, and the result of this was a 60% improvement in performance because of removing that single bottleneck. So one of the things you want to do is when you're focusing on isolating concurrency bottlenecks, you need to look at processes that are waiting. You need to look at call stacks that are waiting, and then try to figure out which calls what are these call stacks actually waiting for, and then optimize from there. So if you see a call stack that's waiting and the system is under high load, more likely it means that there's probably a call stacks that are runnable, that are waiting to call, that are queued up. So that's basically how you identify concurrency bottlenecks. You focus on waiting call stacks, and you focus on runnable call stacks, and you try and identify relationships between the two. And if you can reduce, what we found is that if you can reduce waiting call stacks even just by a small margin, that can have a disproportionately disproportionately huge impact in terms of your metrics. So you can see a huge jump in requests per second because you're eliminating that concurrency bottleneck. Yeah, thank you. That's our talk. You can find the code at these locations. Although I think we do need to, there are a couple of commits that we need to push. We'll push those tonight. And I hope we still have time for questions, or we're out of time.
We definitely have time for questions, and thanks for this amazing talk. I mean, it's an awesome thing that you've done here, and yeah, just wow. So big hand for this.
Thank you.
Thank you.
Yeah, we had one question on Whova, but that has already been answered, both in Whova and live. It was where to find it, where to find the open source, and we have the link here already. So let's see if there are more questions. I think we have 5 minutes for questions. So please, let's see. I'm gonna refresh here and see if there's more things in Whova. Not at the moment, no. So curious question from my side. When doing this project, what surprised you the most when doing this work?
I think that the one thing that surprised us the most was logging. How costly logging is. That was we were shocked. We couldn't believe that it was that costly, and especially if you're doing if you're logging strings. If you're logging strings to disk, that IO, that formatting of that string to a file is really costly. And interestingly, with the OTP21 logger, we haven't yet migrated to OTP 22 or 23. At least with the OTP21 logger, that string formatting occurs even before the overload protector kicks in. So you're always paying for it, because it seems to happen trying to remember the architecture of that system. You have the formatters that format text before it actually hits the handler. And that's what the cost is. The other thing we also found is the other thing that surprised us is that whole idea of focusing on concurrency, focusing on trying to find concurrency bottlenecks, and how much of an impact that has. It pays a lot bigger rewards than, I mean, if you have a relatively mature code base it's been reviewed, and you don't have any silliness in the sequential code. You don't have any n cubed or anything like that. Then you don't want to spend time trying to squeeze performance out of that sequential code, especially if the code looks good. You want to spend time instead trying to find if there are any concurrency bottlenecks that you can eliminate or that you can improve upon. And that usually means processes that are waiting for things, or processes or where you're serializing calls through particular gen servers or particular gen FSMs, gen state M's, sorry.
Thank you. We have another question here from Louis Rascau. What performance penalty is incurred when running it in production?
Yeah, now that depends. What we advise is to use the auto selection. So if you use the auto selection, if you use the auto selection, let's say if you say you're going to profile the top 100 processes by reductions, and you're going to auto select those top 100 processes, we typically saw between 10%, 5 to 10% penalty. So what you normally want to do is you want to do it for a short period of time. So you want to do it in a controlled manner. So you don't want to profile for minutes and minutes. You want to profile for a few seconds, or for a few.
And we also plan to do some work on Flamegraph, in which even in production system we profile periodically, say for 20 seconds or 30 seconds every hour, and not do anything for the rest. So you can have an overall picture of the whole system in production as well without having any cost. Those are in future works as well.
Yes, so that's actually some interesting work. We have a branch that's incomplete where we're trying to model it similar on SASL alarms. So the idea is you set an alarm to say when to start profiling and when to stop. So for instance, if memory goes beyond a certain threshold, you profile for a little bit, so that you don't. So the idea is to have some sort of unattended profiling that can be used in production as well.
Okay, cool. Thank you. I think Mikael Bylund asked a similar question. You already answered that, running on a live system, so that's covered, right? We have another question from Mate Babic. Do you need to compile Flamegraph along with your code, or is it monitoring the system from a separate Erlang node via RPC calls?
Sorry, I didn't. You kind of broke up there a bit.
Yeah, I'll repeat it. So do you need to compile Flamegraph along with your code, or is it monitoring the system from a separate Erlang node via RPC calls?
No, it's monitoring within the system, but yeah, it's monitoring within the system. You have to compile it in and make it available to all the nodes.
And then a comment from Sergei Prokhorov. If not, it would be cool to make a standalone tool similar to Observer CLI eScript.
Okay, we'll definitely look into that. That's a good suggestion.
Yeah, it's cool. You're getting some feedback here, and I think this is just awesome to visualize what is happening in the system, right? I mean, in software, it's so much things that are going on, and we can't really see them, right? So what you've been doing here is really visualizing it, and that helps so much. So this is really, really cool stuff for the community.
Thank you.